Okay, so and there will be a assignment for section 4.4. I'll post it after class. So let's take a look at some of the problems from section 4.3, which we went over yesterday, introducing the log function or log functions. So we'll see, I mean, there's various log functions, but we'll see in the next section, and there's various exponential functions, but we'll see that in section 4.4 that they're really all the same in a certain sense. Okay, so 9 to 66 every third problem. And I assigned these 30, 32, and 76. So number 29, say, well, every third problem. So that would be, let's do a few of these. '24. Hold on. All right, we'll start with 25. So section 4.3. So number 25. So it just asks to evaluate each expression. A, we have the log base 2 of 2. So the log base 2 of 2 is equal to, so it's the exponent, right? It's the exponent for 2. 2 to which exponent is equal to 2? Is equal to 2. 2 to which exponent is equal to 2? Well, 2 to the 1 is equal to 2. B, log base 5 of 1. Well, the base is 5. What exponent of 5, 5 to which exponent is equal to 1? Right, what number is that supposed to be? What number goes here? Right, 5 to which exponent equals 1? If you have a
0.
This is 0, right? A to the 0 is always equal to 1. Okay, it's not 0. Okay, exponential functions are never 0. Okay, a to the 0 is 1. And part C, log base 6 of 6 to the 5th. Right? So 6 to which exponent is equal to 6 to the 5th? Six to which exponent is 6 to the 5th?
To the 5th.
5, obviously. Right? This is essentially the definition of the logarithmic function right here. Log base 6 of 6 to the 5th is 5. And in general, log base b of b to the x is equal to x, because log and exponential functions are inverse functions. So log base b of b to the x is x, and b to the log base b of x is x. In other words, so it looks funny, these expressions, especially this one. Okay, in other words, f of x equal to b to the x and g of x equal to log base b to the x are inverse functions. So f of g of x is the same as g of f of x is equal to x, because a function composed of the inverse function is just the identity function. The identity function is just x. All right, so that's an important property that's going to see some use when we start dealing with equations, solving equations for exponential functions. Okay? These properties of logarithmic functions are going to become important. So actually emphasize that. Save it here. All right. So that's 25. 26. So part A is log base 3 of 3 to the 7th. Well, just in the same fashion that this is 5, this one is 7. Part B, the log base 4 of 64. All right, well, 64, all right, 4 to which exponent is equal to 64? 64 is actually 4 to the third power. Right? 4 times 4 times 4 is 64. So this one is 3. And then C, log base 5 of 125. Well, 125 is 5 to the third. 5 to the third is 125, so this is 3. Okay. So 26. So some other ones that have some more kind of complicated expressions in them. 29. A log base 3 of 1 over 27. Right? Well, 27 is 3 to the third. Right? So 1 over 27 is 3 to what exponent? Which exponent goes up here? If you want 1 over 27.
1 over 3.
Negative 3. Right, to get reciprocals with exponents, you negate them. So it's x to the minus n is equal to 1 over x to the n. That's the that's the way you deal with you change a negative exponent to a positive exponent is doing that. Remember way back in chapter P, we were looking at simplifying these product expressions like a to the 6, b to the minus 7, c, and then b, a to the minus 1, d or c or something like that. And we had these things, right? And then what you did is you moved the negative exponents from top to bottom, right? So this was a to the 6, and then the a, and then the c, and then the b to the 7th goes down here, and then the c, and these c's canceled, and you had a to the 7th over b to the 8th. Remember that business? So that's a sort of more general usage of this property. Okay, so negative exponents give you reciprocals, essentially. All right. 29b, log base 10 of the square root of 10. I have a funny story about the square root of 10. Right, well, square root of 10, how do you write the square root of 10 as 10 to some exponent? Is 10 to which exponent? What goes up here? How do you change a square root to an exponent?
To the second?
To the
First?
1/2. All right, so the nth root of a is a to the 1 over n. So, the root notation is really, so I mean, this sort of notation isn't really used much. So like third root, fourth root, fifth root, this square root symbol with the n in here. The only one that's really used very much is the square root symbol, but it's the same thing. It just means 10 to the 1/2. This is a to the 1 over n. So the fractional exponents come from square roots. So like the square root or the qth root of a to the p is a to the p over q. Right? So that's what the rational exponent means. And it's a lot nicer notation than this. This is quite clunky, and this is much nicer. Okay, so that's 10 to the 1/2. So that's log base 10 of 10 to the 1/2. So that's 1/2. C log base 5 of 0.2. Well, 0.2 is what? Is a fraction that uses 5. Zero 0.2 is what as a fraction? It's 1/5, right? Which is equal to the log base 5 of 5. Well, since 1/5, all right, since 5 is 5 to the 1, 1/5 is 5 to the minus 1. Right, that's how you do a reciprocal, 5 to the minus 1. So this is minus 1. Let's try another one of those. So 30, it's kind of similar to that. Actually, there isn't another one like that. Oh, I guess 33 is kind of like that. Log base 8 of 0.25. Is that a typo? I think that's gotta be a typo. Let me see. This number 33 and 4.4. Or 4.3. No, I guess it is not. So log base 8 of 0.25. Well, 0.25 is 1/4, right? Well, first of all, 8 is 2 to the third. And 4, right, is 2 squared. So 8 to which exponent gives you 4? Well, you have to take the third root of 8 and then square it. So 8 to the 2/3 is 4. All right, this is the third root of 8 squared is equal to 4. The third root of 8 squared is equal to 4. But this is the same thing as 8 to the 2/3. So 8 to the 2/3 is equal to 4. So 8 to which exponent is 1/4? How do you get the reciprocal? What do you do to the exponent? What do you do to the exponent to get the reciprocal? 1/4.
Make it negative.
Make it negative. So this is negative 2/3. B. ln e to the fourth. What does ln mean? ln is the log base e. So remember, log base e. So this is the log base e of e to the fourth. So going back to the discussion above, right? Because the exponential function and the log are inverse functions, that just gives you 4. So e to what exponent give you e to the fourth? 4. This is probably the most commonly used logarithm, ln. Again, they're all the same in a certain way, in a certain sense, which we'll see later. C is natural log 1 over e. 1 over e is e to the minus 1. Right? And then again, natural log is log base e of e to the minus 1. So that's just minus 1. So which ones did I assign? 30 and 32. So 30 and 32, there's some nice, nice examples in there. So in 32, by the way, they use the ln notation. Remember, ln is log base e. When they just write log, that is log base 10. And then when they write lg, that is log base 2. Although I don't think they use that notation in this book, lg. But they do use log in natural, ln, natural log. Okay, so that notation is used, in some of these problems. And then, of course, you can always, stick these things into your calculator, but the calculator only has log base 10, that's the common log, and natural log. It might have an LG button. I don't think I've ever seen one that has log for any base built into it. So how do you evaluate other logs with other bases using your calculator? Well, we'll see that in the next section. It's quite simple, actually. But we'll get to that in a little bit. All right. So I also assigned, so it was 30, 32, and, 76. What is 76? Oh yeah, it's about domains. So let's look at some domain problems. How about 75? So find the domain of f of x equal to the log base 3 of x squared minus 1. Okay, remember the log function, any log function, its graph looks like this. And this is 1 here. So this is y is log base b of x. So the domain of any basic log function, log base b of x, is the interval from 0 to plus infinity, not including the 0. Right? So because exponential functions are always positive, right, with positive sort of coefficient in front, as long as they have a positive coefficient in front, the exponential function is always positive. It's never 0, it's never negative. Or if you have a negative coefficient in front, it's always negative and never 0, never positive. So the sign doesn't change on an exponential function. So for a log function, because the exponent b to the exponential b to the x is always positive, the range is 0 to plus infinity. So the log being the inverse function, the domain is 0 to plus infinity. Okay, so how about this function here? This function f of x. Well, for f of x to be defined, we need that x squared minus 1 is bigger than 0. How do we do inequalities of quadratics? How do we do inequalities of quadratics? So we had a whole section on how to do this kind of thing. It came up again later on, and I noticed that people forgot about that section. So I move the 1 over here, right? And then what?
Square root both sides.
Well, if I took the square root of both sides, what happens? Right? You don't know which, if this is positive or negative. I mean, it's essentially you can't solve quadratic inequalities or polynomial inequalities by doing square roots. Okay, it's not like solving the equation. This one actually you can, although it's a lot less clear and it doesn't use the general technique. You have to factor, right? Put the zeros on the number line, so those are not part of the solution because we want to be greater than 0. And then you test the intervals, right? Like x equal to minus 2. So this is positive here, so that's part of the solution. X equal to 0, negative and positive, negative, so it's not part of the solution. And then x equal to 2, they're both positive, those factors, so it's positive here, so that is part of the solution. All right, so the domain is minus infinity to minus 1, union 1 to plus infinity. So we discuss a lot of different techniques about how to do mathematics, how to solve these equations, how to work this kind of problem, how to solve this kind of word problem, so on and so forth. You learn different techniques when you're doing mathematics. But there's one technique that's the greatest technique of all. The one technique in mathematics that is the greatest technique of all is the following. When you learn something once, you learn it once, right? And try to remember that you learned it. Like, oh, where did I see this kind of thing before? I know I've seen it before. Now let me think back to it. And you should remember, the basic techniques that went along with it. So, I know that's kind of an annoying answer, but an annoying answer to an annoying question, but when you learn things, if you can somehow commit them to memory, that's a good thing. All right, how about number 73? So, what's the domain? For fx equal to the log base 10 of x plus 3. Well, again, in order for this to be defined, we need that x plus 3 is bigger than 0. Right? It's got to be positive. Again, the argument always has to be positive. Now, with a polynomial of degree 1, a linear polynomial, and you have an equation with a linear polynomial, here it's just like solving the linear equation. Right? It's just with your quadratic polynomials and cubic polynomials and so on and so forth, when you have inequalities, those are solved by factoring. By factoring, putting the roots on a number line and then testing the intervals. Like with linear polynomials, however, now you don't have to do that. So x bigger than -3. So here's -3. The x is bigger than that. So -3 to plus infinity. Here's a similar question. Find the domain for fx equal to the natural log of x squared plus 1. Well, again, we need that x squared plus 1 is bigger than 0. But this doesn't factor. Right? It doesn't factor. That's an irreducible quadratic. Right? So the irreducible quadratics are either always positive or always negative. Right? This one, so there's no roots here, or doesn't factor. So it's either always positive or always negative. Well, this one is what? Always positive or always negative? Well, 1 is positive and x squared is bigger than or equal to 0. So when you add them together, right, this is positive. All right, so the domain for fx equal to natural log x squared plus 1 is all real numbers. Right, all real numbers. You can plug whatever real number, even negative ones, in for x, and the x squared plus 1 will be positive, right? So if you take like x equal to -2, this is, then x squared plus 1 is 5. Right? It's a positive value. So you can always take the natural log, or the log, or whatever log, of a positive value. All right. What else other sort of things do we have in here? Let's leave the rest of that. Those are similar to the homework questions, those that we just did. Let's move on to section 4.4, which gets into some of the important properties of the logarithm function. Again, by the way, the log function seems to be confusing sometimes. So it needs a little extra time on your part. So make sure you spend that extra time and really try to, to learn what goes on with the logarithm function. So properties of logarithm functions. In the book, they call it laws of logarithm functions. I don't think I would call it a law. there's no civil code of law for logarithm functions. It's the properties of the logarithm function. So the following three properties work for logarithms of any base. Okay, I'll just leave out the base for now. So that the properties look less cluttered. So there's the following three properties for logarithm functions, and that's it. There aren't any more than these three that I'm about to write. So the log of a times b is equal to the log of a, so for whatever base you might have, plus the log of b. The log of a product is equal to the sum of the logs. Right, so here's maybe a first point of confusion. It takes multiplication, turns it into addition. So the log of a times b is log of a plus log of b. Okay, 2. The log of a over b, well, it's very similar to what we just wrote. That's the log of a minus the log of b. 3, the log of a to the r is r times the log of a. So these are three algebraic properties. There's other properties that we're going to talk about later. Okay, but these are like the algebraic properties that are important for using logarithms to solve equations. Okay, so the algebraic properties, there's just these. There's nothing else. Okay, you will be tempted to do the following. So the following expressions do not have alternative. Well, do not equal anything special. the log of a plus b. The log of a plus b is not log of a plus log of b. Again, nothing distributes over addition. Log doesn't distribute over addition. Exponents don't distribute over addition. Fractions don't distribute over addition. Well, addition distributes over a denominator. Addition in the numerator distributes over a denominator. But that's, again, just multiplication distributing over addition. Multiplication distributes over addition. Nothing else does. A plus b squared is not a squared plus b squared. The square root of a plus b is not the square root of a plus the square root of b. The log of a plus b is not the log of a plus the log of b. Absolutely nothing, except for just plain old multiplication, distributes over addition. Okay, so if you ever see log a plus b, well, that's it. There's nothing else you can do with it. You have to deal with it as is. Log of a plus b is not the log of a plus the log of b, because the log of a plus the log of b is the log of a times b. And a plus b and a times b are just not the same thing. Log of a times the log of b. Log of a times the log of b. Well, I mean, you might be able to use this in some way. So maybe I'll leave that one out. You might be able to use this in some way, but probably not. What else? There's another one. The log of a minus b. I'll just leave it at those two. All right. So, example. Use the three properties above to what's known as expand the logarithmic expression. And by expand, we mean take out all the multiplication, division, and exponentiation within the expression. To take out all multiplication, division, and exponentiation from within the arguments of logarithms. So you can have a logarithm that has multiplication inside of it, or has division inside of it, or exponentiation inside of it, and so you want to expand that. Okay, so that means remove all of the multiplication, division, exponentiation from the inside. So, for example, log, so whatever base you might have, x to the third y squared over z. Okay, well, first of all, I have a division here, so I'll use that log a over b. So let me copy these and put them next to us down here so I can remember them. Okay, so using log a over b is log a minus log b. Here we have log x to the third y squared minus log z is equal to log x to the third y squared divided by z. Going further, Log of a product, log of A times B, is log of A plus log of B. So I'll use that here. So this is log of x to the third plus log of y squared minus log of z. And then using this property here, log of a to the r is r times log of a, bringing that exponent inside the log down to a coefficient in front of the log. This becomes 3 times the log of x plus 2 times the log of y minus log of z. And that would be a final answer. Okay, we have expanded the logarithm expression. Okay, we've expanded this logarithm expression. We've taken out from within the arguments of the logs all of the multiplication, division, and exponentiation. So here you just have x, here you just have y, here you have z. There's no exponentiation, division, or multiplication within those arguments for the log function, whereas here you've got a lot of that. Right? So that's a final answer for this expansion. Similar to this, log expressions. What if I had something like this? Log of x plus 1 to the third, x minus 1 squared, over x squared plus 1. Suppose I have something like that. And I want to expand it. Well, it's exactly the same as what I just did. It's exactly the same as what I just did, except, here I'm replacing x with x plus 1, y with x minus 1, and z with x squared plus 1. So z to the first is just x squared plus 1 to the first. Y squared is x minus 1 squared, and this x to the third is x plus 1 to the third. So if you were to do this expansion, first I would use that division identity. Log of a over b is log of a minus log of b. Right, so this is log of the numerator minus log of the denominator. Right, log of the numerator minus log of the denominator. I can't do anything else with this. Nothing else. Right, that one's as simplified as it's going to get. Simplified as expanded as I get. Why can't I do this? Log base, or log of x squared plus 1 is equal to 2 times log of x plus 1. This is wrong. Why can't I do that?
The 2 shouldn't affect the 1.
Right, exactly, right? It's log of a to the r, where r is over the whole a. The exponent is on top of all the a. Then you bring down the r, right? So this would mean, this actually means log of x plus 1, that whole thing there, squared. Right, so this is actually log of x plus 1, the whole thing, squared, which is the log of x squared plus 2x plus 1. I know some of you are thinking, well, x plus 1 squared is x squared plus 1. No, it's not. Exponentiation doesn't distribute over addition. Nothing distributes over addition. Okay, nor the log. So that's a done deal right there. That one. All right. So coming back to this. This one's a done deal, but this one I've got a multiplication inside there, right there. Right, this is multiplication. So I want to remove that. So this becomes log of x plus 1, the whole thing to the third, plus the log of x minus 1, the whole thing squared, minus the log of x squared plus 1. This, I have the 3 up here, so that comes down front. Here I have an exponent of 2, so that comes down in front. So there's the final answer. It's just like this problem. Instead of using just a single letter, x to the third, y squared, z, I have some more complicated polynomial expressions. So x plus 1 to the third, x minus 1 squared, and then x squared plus 1 to the first. So this and this are really the same thing, and you see that the answers are the same. This x corresponds to the x plus 1, this y corresponds to the x minus 1, this z corresponds to the x squared plus 1. If I did something like this. What about that? Well, that whole square root thing there, right? That whole square root is essentially this expression, x to the third, y squared over z to the 1/2 power. So now using this one again, so let's bring this with us. All right, it might be nice to write that down on a like piece of paper and leave it beside you when you're working these problems, just so you don't forget them. And here the 1/2 comes out front. Right, so using this property, log a to the r is r log a. So this square root is just the whole thing is an exponent of 1/2. So now now I've got this same expression here, log x to the third y squared z. Right, that's this one. 3 log x plus 2 log y minus log z. So it's equal to 1/2. 3 log x plus 2 log y minus log z, just like before. But now the whole thing is multiplied by 1/2. How about this? So we want to expand that. Again, what does expand mean? Take out all the exponents, multiplication, and division from the inside of the logarithm. That you can using these properties here. Right, so, well, again, the square root, right, is a 1/2 exponent. So it's 1 minus x squared to the 1/2. Right, so that 1/2 come out front. What else might I be able to do here? Yeah. What else could I do with that? There's one more thing I can do here. Well, 1 minus x squared, that factors, right? 1 minus x, 1 plus x, right? So a difference of 2 squares there. So this is 1/2 log 1 minus x plus log 1 plus x, like that. So, if you want, you can distribute that fraction through. So 1/2 log 1 minus x plus 1/2 log 1 plus x. So that would be a final answer there. Or this one, whichever one. Or you can put the whole thing as a fraction over 2. Okay. What else? What other kind of examples can we do here? Oh, how about something like this? For example, I'll just make them up here. All right, well, here, this is a degree 3 polynomial, and sometimes we know how to factor it. This one we can use that grouping technique. So it's x squared times x minus 1 plus x minus 1, like that, which is equal to, factoring out the x minus 1 times x squared plus 1. And that doesn't factor any further because the x squared plus 1 doesn't factor anymore over the real numbers. So we just have that the log of the product is the sum of the logs. So we have, at the end here, removed all the multiplication that we could from the inside of the logarithm argument by factoring and then pulling apart the factors by summing the logs. Okay. So when you're doing these problems, I would write these down, on a piece of paper and leave it next to you while you're doing some of these problems to remind yourself of what those are rather than like guessing at them. All right. So those are the three algebraic properties of the logarithm function that are important. And the last sort of important property or formula for logarithms is the change of base. Change of base formula. So if you have the logs, so like I was saying, all the logs are really kind of the same. The log base b of x is equal to, well, the only log buttons that you have on your calculator are natural log. Where'd my calculator go? Typically, are natural log and natural log ln and common log base 10. Okay, or maybe you have the log base 2 on there, or in some weird models you might have log base b for whatever b that you wanted. But the log base b of x is essentially the log of x over the log of 10, where this is the log base 10. Also, you have the log base b of x is equal to the natural log of x over the natural log of b. Or for any other base, it's the same thing. Log base b of x is the log base c of x over the log base c of b. And in each case, these are all constants, the denominators of these fractions. The denominators of those fractions are constants. The numerators are variable. Right? X is variable, so the log of x is variable. But the log of 10 is just a number. The natural log of, not 10, natural log of b. Log of b is a constant, so the log of b is a constant. Natural log of b is a constant. Log base c of b is a constant, and all those things. So in this sense, all the logs are really the same. They're just a constant multiple of the other logs. The log base b of x is just a constant multiple of the log base 10 of x. So in this sense, all log functions are the same. Right, the log base b of x is equal to k times the log of x, right, for k equal to for a constant k. Okay, so they're really not much different than the other. All right, so now, for example, so we know that the log base 2 of, I don't know what's our favorite power of 2 here, 128, right? Log base 2 of 128 is the log base 2 of 2 to the 7th, right? So it's just 7. All right, let's check on our calculator. The log of 128 over the log of 2, well, it's going to be equal to 7. And the calculators are usually hardwired to detect that kind of thing. So it won't give you any like errors, rounding errors when doing that kind of thing. So log of 128 divided by log of 2. And we know it's supposed to be 7. So you got to use this reverse notation. So 128 log, and you get this number 2.107 something something, divided by 2 log equals 7. Right, and you don't get any rounding errors when you do that. Right, calculators have some kind of subroutines in them that detect that kind of thing. So log 128 divided by log 2 is the log base 2 of 128, which we know to be 7. Or, you could use a natural log. Natural log 128 over natural log of 2. So 128 natural log divided by 2 natural log is 7. Okay, so natural log 128 divided by natural log 2, 7. Common log 128 divided by common log 2 is 7. Same thing. So now it's easier than before. So that one tricky example we had before, the log base 8 of 1/4 was equal to minus 2/3. Right, so this was from the previous section. Right, because 8 to the 2/3 is equal to 8 third root of 8 squared. Third root of 8 is 2, squared is 4. 8 to the 2/3 power was 4. But let's plug that into the calculator. So on our calculator, so remember, 2/3 is 0.6666666, blah, 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 0.6 repeating. Log base 8 of 1/4 is log of 1/4 over log of 8. So let's calculate that. So 1/4 is 0.25. So 0.25 log divided by 8 log equals, right, negative 2/3. Of course, the calculator only has, so this one is, 32 decimal places of accuracy for 32-bit operating system, I guess. So it rounds the last one off there with a 7 instead of a 6. But that's negative 2/3. And the log base 8 of 1/4 is also equal to, you could use the natural log button. So 0.25 natural log divided by, oh, it's time to go. 8 natural log equals, 0.6666666, so that's negative 2/3 again. Okay, so that's the change of base formula. So calculating logs with other bases is no longer a problem. It can be done on the calculator easily enough. Okay. All right, so that's it for today. The assignments that were due tonight, we'll have them due tomorrow night. And other than that, have a good weekend, and I'll see you on Monday.